So our final talk of the session is going to be from Jinbo, coming to us from Chicago. So I'm going to leave the floor to him.
Okay, yeah, thank you very much, and thank you for the invitation. So in this talk, I'm going to talk about abyssal folding. So abyssal folding is a very old problem, has been studied for a few decades. So the problem definition is very simple. Given a protein sequence, we wanted to use computational methods to figure out the 3D conformation of this protein. It's a very challenging problem, has been studied many years, and there's also very big demand. And so currently I'm running a web server called RaptorX, and the RaptorX now each month will process about 10,000 prediction jobs. Many proteins that can be modeled by templates. The templates are just similar proteins with solved structures in the PDB, but there are still many proteins which couldn't be modeled by template-based method, like for example, the membrane proteins. We don't have good templates for many membrane proteins. So in this talk, I will focus on the case when we don't have good templates. So this problem is a very challenging problem, and although it has been studied for many years, but before the progress is very slow. Fortunately, in recent years, now we are making very good progress on this problem. Before, the most popular method is called the fragment assembling. And recent years, now we have an emerging method called the contact-based folding. And this contact-based folding is much more promising than the fragment-based assembly. So this contact-based folding depends on the context. So we do contact prediction, and then using the predict context to restrict the search space. And then as long as the contact prediction is accurate, then we can do the folding much better than before. So first, I'm just briefly define what's a contact. So suppose we have a small protein here with 4 residues. Then we calculate distance between any 2 residues. Say, for example, we can calculate the C beta distance. If the distance is less than 8 angstroms, then we just write 1 in this matrix. If it's bigger than 8 angstroms, then we write 0. So we have such a binary matrix to represent this protein. So this binary matrix is called the contact matrix, and it's very sparse. The number of contacts is only linear with respect to the sequence length. So this is the contact definition. Then the problem becomes, given a protein sequence, we wanted to predict such a contact map first. After we have such a contact map, then we can rebuild or reconstruct the 3D model of this protein. So this is the contact-based folding, and then the key issue is how we can predict the contact map accurately. The first breakthrough on this contact prediction problem is called co-evolution analysis. This method is based on the one observation. So if 2 residues they are close in the space, or they are in contact in the space, then it's likely they will co-evolve, which means when one residue mutates, then the other one is also likely to mutate. So based on this observation, then we can do co-evolution analysis. So the co-evolution analysis starts from a multiple sequence alignment. So given a query sequence, we just go to the sequence database, we find all the sequence homologs and build a multiple sequence alignment. So based on this multiple sequence alignment, then we can look for the highly correlated columns. These highly correlated columns, they correspond likely they correspond to the co-evolved residues. So this is the basic idea of the co-evolution analysis. Thanks to the high throughput sequence, now we have tons of sequences. So now this co-evolution analysis method now becomes effective when you can have when you can find many sequences for the query protein. So this is the first breakthrough for the contact prediction. So this method works, as I said, works for some very large size protein family. Say if a protein family has 1,000 sequences, then likely this method can give you some very accurate contact prediction. But unfortunately, when we look at those protein families without solved structures, and actually many of them, I would say half of them has only about 100 sequences, which means in this case, we couldn't apply the co-evolution analysis. So we have to develop other better methods. So the co-evolution method is purely based on sequence. It's only we use very little structure information. They only assume the contact map is sparse. So this is prior information by some convolution analysis method used. But actually, we have other structure information which we can make use of. For example, we know a protein structure actually is a 3D compact geometric object, and usually in the minimal energy state. And there are also a very limited number of different protein folds. And the two proteins, even if they have different folds, likely they will share similar structural motifs. So we should exploit this kind of structure information to develop a better contact prediction method. So here I show you one example of the contact map. So in this example, the black box indicates a contact. So you can see here there are some patterns in this contact map. And the contact map, this matrix is not a random matrix. So actually, we can extract some patterns from the contact maps. So here are some frequently occurring patterns in the protein contact maps. And I also did some simple statistics. So I look at the small submatrix in the contact map. For example, I look at the 3 times 3 submatrix, and I calculate the occurring frequency. So here I show you the top 20 most frequently occurring submatrix here. So the occurring frequency of this submatrix are very they are not uniformly distributed. So here I show you the top 20, and I also look at the membrane proteins. So look at the membrane proteins, the submatrix occurring frequency. It turns out, so both membrane proteins and the non-membrane proteins, they share very similar contact occurring patterns, although their sequences are very different. But when we look at the contact map, they share similar the contact occurring patterns. So we wanted to develop an algorithm to make use of this kind of patterns to improve the contact prediction. So here's why we use the deep learning. So we use deep learning. We try to learn what a protein like contact map by using deep learning, and we wanted to model the contact occurring patterns or the structural motifs. And we wanted to exploit as much global structural information as possible in our learning algorithm. So this is different from the pure convolution analysis, because pure convolution analysis is mostly just based on sequence information. So this problem is kind of similar to the image semantic segmentation problem. So if we treat a contact map, the contact matrix as an image, but actually, so we wanted to assign a label to each pixel in the image. So it's very similar to the image semantic segmentation. Then we can borrow some ideas from the images classification. So we predict all the contacts of single protein simultaneously. And so this is very important. So this is different from previous supervised learning method. So previous method, they will just predict one pair of residue independent of the others. But here we predict all the whole contact map as a whole. So by doing this, then we can capture the global information, and we can easily model the contact occurring patterns in our algorithm. And finally, our deep learning can also integrate the many different protein features. So this is the idea of our deep learning method. So here I'm going to show you some details of our deep learning method. So again, we also started from the multiple sequence alignment. And then from this multiple sequence alignment, we can get extra 2 types of information. The first one is called sequential feature. So sequential feature is just a one-dimensional feature. So either at each column, we can get some information from this multiple sequence alignment. For example, we can get the single position conservation information. And we can also do the second structure prediction for each position. So this is a sequential feature. Then we also have the pairwise feature. So pairwise feature, we are just look at the two columns. For example, you can calculate the correlation and calculate the mutual information between 2 columns. And you can, so this is a pairwise features. Then we fit these 2 types of features into our deep learning network. Then deep learning will predict this matrix. So this is the contact matrix. So this is the input and the output. And here I'm showing you the network architecture. Since we have 2 types of information, so we use 2 different residual networks. So residual network is just one type of one variant of convolutional neural network. So to deal with the sequential feature, we apply the one-dimensional convolutional neural network here. So this is the 1D information. And to deal with the 2-dimensional information, the pairwise information, here we apply the 2-dimensional convolution neural network. And to combine them together, then here we do a transformation here. So, so from this sequential feature, then this sequential information, then we do an operation similar to order product. We convert this sequential feature into the pairwise feature here. Then we just merge them together to get a new pairwise feature and fit them into the 2D residual network. So this is the network architecture. If you want to know the details, yeah, please go to read our papers. So this is our network, and so here I just show you the one-dimensional convolution neural network. Once you understand this one-dimensional, then you can easily understand the two-dimensional. So here we have an input which is a sequence. So then we do convolution at each position. Like here, in this example, when we do convolution at this position, we just look at a small window like here. So we here, by doing one convolution, we just summarize the information in these three positions. So we get the new neurons here. Then we can do convolution at each position, and then we can do many layers. So this is the one-dimensional convolution neural network for sequence modeling. So by doing the one-dimensional, then we can capture the sequential local context for one position. When we use more and more layers, then we can capture a larger and larger range information for one position. So this is the convolution. And so before we propose the convolution, there's also another group. They propose the deep belief networks. But these deep belief networks didn't work very well. The major reason is because the deep belief network predicts context one protein one by one. So they just predict one pair of residues and independent of the other pairs. But by using the convolution, then we can predict the whole content matrix simultaneously. So this is a very big difference between the deep belief network and the deep convolution neural network. And this is also why the convolution neural network works much better than the deep belief networks. So this means by using the convolution, then we can use more global information, but the deep belief network can only use the local information. So this is a major difference. Okay, now I'm going to show you some results. So the first result is on the CASP11 test set. So CASP11 has 105 test proteins. So here we, in this table, I show you the accuracy on some top predictions. So in the table, L is the protein sequence length. When we here L over 10 means when we look at the top L over 10 predictions, and the numbers here are the accuracy on this top L over 10 predictions. And we also have three different groups here: short, medium, long. So this means we separated the context based on the sequence distance of the two residues. So if the two residues they are far away from each other, then we say this kind of contact is called the non-range contact. And non-range contact is the most difficult to predict, but it is also the most useful for protein folding. So here we just focus on the accuracy on this non-range contact prediction. So when we look at the top L over 10, so in this table, in total, we have 5 methods. So these are our methods. And these top 3, they are pure co-evolution method. And this is a supervised learning method. So the metacycle will use the output from these 3 programs and do a supervised learning and use a neural network to do a supervised learning. So these 5 methods. So from here, you can see on this test set, so the co-evolution method, the accuracy is about 40% when we look at the top L over 10 predictions. But our method can double the accuracy, so we can get 80%, and so much better than all the other methods. And the advantage is even larger when you look at the top L, when you look at more predictions. Like say, when you look at top L, so the co-evolution method is only about 20%. Then we can do 55% accuracy. So we can significantly improve the contact prediction accuracy. This is CASP11. The reason is because many targets in the CASP11 they don't have many sequence homologs. So when we don't have many sequence homologs, then the co-evolution method doesn't work very well. And here is another test set. So CAMIA. CAMIA is similar to CASP, but it's an online benchmark. It's also blind prediction, but it's online. And so the CAMIA target is even harder than the CASP. So because here we just look at the hard targets. So again, let's look at the top, the long-range contact prediction accuracy. So now you can see here, for these three pure correlation methods, the accuracy is 20 to 30%, but we can do 69. So now it's more than double of the accuracy of the correlation method. And so this is the accuracy on this even harder test set. So this is the CASP-12 official ranking. So the CASP-12 was held in 2016. And so this is our method. So our method is ranked #1. And this is the pure correlation method. So pure correlation method doesn't work very well on the hard targets. And this method, they use some supervised machine learning, and some of them also use deep learning method. And so when we were participating in the CASP-12, actually I was implementing our algorithm. So I started to implement when CASP-12 started, and I finished implementing when CASP-12 ended. So I didn't. So I didn't get the full implementation of algorithm was not applied to the CASP-12, but still we did the best. So we performed the best in CASP-12. But now our algorithm our accuracy is much better than what in CASP-12. So I just show you, so now we can do much better counter prediction, right? So our final goal is to do the 3D modeling. So the question is, now we can improve the counter prediction, so can we also improve the folding, right? This is our final goal. So we did some simple test. So we fit our predicted context as a distance constraint to a software CNS. So CNS is developed for the NMR structure determination. So CNS we take the NMR data as input and output a 3D model. Here, then we fit our predicted context as a distance into CNS, and then also we output a 3D model. Then we evaluate the quality of a 3D model by comparing it to ground truth. And here we use two metrics. One is RMSD, the other is TM score. So RMSD will measure the difference between our model and the ground truth. And TM score will measure the similarity between our model and the ground truth. So TM score ranges from 0 to 1. When TM score is bigger than 0.5, then likely the 3D model has a correct fold. So we random choose 550 proteins from our test set, and then we do folding, and then we find out. So among them, about 70% of them have TM score bigger than 0.5, which means so we can fold about 70%. We can produce the correct fold for about 70% of our test proteins. And if we require high accuracy, for example, if we wanted to TM score to be larger than 0.8, then we can get 20% of them. So this is a test set on this randomly chosen test set. And we also look at the CASP-12 hard targets. In total, there are 37 CASP-12 hard domains. So among these 37 hard targets, so we can predict correct fold for 20 of them by using our algorithm. And the best CASP-12 groups can only do so for 11. And here we only use our prediction algorithm. We don't do any folding simulation. But the best CASP-12 groups, they using predicted context and also use template information and also use the folding simulation. But they can only do 11 of them. So which means by using the deep learning, we can significantly improve folding. And if we also look at the pure correlation method, if we fit the context predicted by the pure correlation method to the CNS software web, and we couldn't get any correct fold. So which means if you wanted to use the pure correlation, you have to combine the prediction from pure correlation with other methods. You cannot simply just use the pure correlation method to do the folding. So this is the results for soluble proteins. But as I mentioned at the beginning, so membrane proteins, we couldn't use template-based modeling for membrane proteins because we don't have many solid structures for membrane proteins. But membrane proteins are very important for drug discovery. So can we apply deep learning to membrane proteins? We know that deep learning requires a large amount of training data, right? But we don't have many training data for membrane proteins. So fortunately, we found out actually we can apply the same deep learning model to membrane proteins. We don't need to use any membrane proteins to train our model. We just use non-membrane proteins. We just use other proteins to train our model. Then just simply apply the deep learning to membrane proteins, and it works very well. So here I will just show you some simple brief results, and you can go read our papers for details. So we did some experiments. So here we did 3 experiments. So here we train our model using the only membrane proteins. We only have about 500 different membrane proteins to train our model. Then we also train our model using all the non-membrane proteins. So we don't use any membrane proteins to train our model. And then we also then finally we use a mix of the membrane proteins and non-membrane proteins to train our model. So let's look at the counter prediction axis here. So look at these 2 methods. So by using all the non-membrane proteins, then we can get accuracy better than using the membrane proteins. So we don't need any membrane proteins to train our model. The reason is because we have many more non-membrane proteins than membrane proteins. So we can get a better deep learning model than when you just use the membrane proteins to train the deep learning model. And these accuracies are much better than the other methods. And when you mix them together, mix the membrane protein and non-membrane proteins, then you can improve the counter prediction accuracy by a few percentage. So this is the results for membrane proteins. And we also have the folding results on membrane proteins. So this results was, so we got this results about 1 year ago, so it's pretty old, but now we have much better results. So here, so we fold on the 500 membrane proteins, and we also, so these are results of our 3 strategies. And we also compare with the pure co-evolution method, the system plate, and also the one shallow neural network method, meta-side curve. So we can get, say, for example, when we look at using the 6.5 angstrom as the cutoff to determine if a model is good or not, then we can, like the system plate can get 49, and the meta-side curve is 64. But using non-membrane protein to train our model, we can get 138, much better than them. And then when we use the mixed strategies, then we can get 169. So this is the model quality in terms of the RMSD. And when we use the TM score to measure the model quality, then we can get the correct fold for about 288 of them, and it's much better than the CCM plate. Yeah. So this is the results, folding results on membrane proteins. And now, I guess now our results is much better than this, than this number. So here I show you one example. So this is one Camille test target was released last year. And this is the membrane proteins. It has 200 amino acids, more than 200. And this protein, this target also actually has many sequence homologs. It has more than 1,000 sequence homologs. Then first, let's look at the counter prediction accuracy. So here, this is our accuracy. And then we compare with the meta-side curve and the 2 pure co-evolution method. So from here, you can see, even for such a protein with 1,000 sequence homologs, our accuracy is still much better than the pure co-evolution method for the counter prediction. And this table shows you the 3D modeling accuracy. So we get this result from the Camille website. So each server can submit up to 5 models. So here are the results of our 5 models. So this is the last column is the TM score, and this column is the MSD. So our model has MSD about between 2 and 3 angstrom, and the TM score is about, so it's the best is 88, 0.88. So it's a very high accuracy model. And then after our model, then there's no data. So David Baker's model. So David Baker's model has about the MSD is 5 angstrom. And then TM score is 0.69, so it's much worse than our model. So, and we don't use any template information. We just do the counter prediction and build a model. And this shows you the superimposition between our model and the ground truth. So you can see the superimpose very well. So this results on one membrane proteins. Okay, and so our method can also apply to the complex counter prediction. So yeah, we did a very large scale study, and so we test on thousands of complexes and then compare our method with this our method and with some this pure co-evolution method. So one point, so it's indicate the quality of our method and the co-evolution method. So you can see for most test data, so this point is the line below this diagonal line. So this indicates our method is better than the co-evolution method. So we don't retrain our model. We just train our model on the single chain proteins. So we don't train our model use any complex data. And then just directly apply our model to do the prediction. So we can get a much better prediction than the co-evolution method. So here we just summarize. So So by using deep learning, so we can do the very fast and accurate aberration folding. And so we just run our algorithm on one Linux workstation with one GPU card and 20 CPUs. So we can fold the protein within 30 minutes to a few hours. And so the deep learning method outperforms the pure correlation method greatly. So no matter how many sequence homeworks you can find. So this method also works for membrane potency and for complex contact prediction. So yeah, so I think there are lots of interesting work to be done. So we just started this deep learning method. So we just published the method early in last year. So still many work to be done. So we are still exploring if we can develop better, more accurate method for contact and distance prediction or not. So we are trying to incorporate more physicals into our model. And then regarding to the 3D model reconstruction, and so right now we just use the software, we use CNS. But CNS was originally designed for experimental data. It's not designed for our prediction data. So I think we should be able to develop better algorithm to rebuild the model from our predicted information. And we also can combine the predicted information with some physical force fields to see if we can improve the folding accuracy or not. And especially for membrane proteins, here, when we do the folding, we don't use any membrane protein specific information. So I think if we combine some membrane protein specific information into our algorithms, then it's possible to further improve the modeling of membrane proteins. And although I just show you, so our method works much better than pure correlation method for complex contact prediction, but actually the overall accuracy is still not very good for complex. The reason is because for many complex, we couldn't find any sequence homologs for the complex. So there are only 1 or 2 sequence homologs for many. It's very challenging to find a sequence homologs for complex. So we need dozens. We need at least dozens of sequence homologs to be able to be effective for our algorithm. Okay, so I will stop here. Thank you very much.
So I think we have a little bit of time for questions. Go ahead.
So I was thinking about your results on the membrane proteins, and I had a couple questions. First, I was actually amazed that you were able to even get better than random prediction just training on membrane proteins, given the small number of membrane proteins in the large model. I was wondering, so you do any kind of pre-training or use a smaller model for that part? And then the other related question was for the mixed one, where you saw that huge improvement. Were you upweighting the membrane proteins in any way?
Yeah, it's a very good question. Yeah, so when we only use membrane protein trial model, then we have to use a much smaller model. Otherwise, it will overfit. Yeah, yeah, but still, it works better than other methods. And so, yeah, so when we use the mixed strategies, then we use a very big model. Yeah.
And we had one other question in the corner.
So for the membrane part, did you have only 500 training data?
Yeah, so in the PDB database, there are now about 3,000 membrane proteins, but many are similar. So we remove those redundant. So finally, we have about 500 different membrane proteins.
Great. So let's thank the speaker again. So